Inert versus labile complexes. Inert complexes are unreactive or very slow to react, whereas labile is the exact opposite of that. They're complexes that will react very quickly. Now, here's an example of an electron configuration that matches an inert complex, and here's an example of one that matches a labile complex. In this case, we both have low spin or high field complexes, but here we have a D6 complex and here we have a D7 complex. In our D6 case, you'll notice that the T2G orbital is completely filled and the EG orbital is empty. Whereas over here we have a completely filled T2G orbital as well, but now we have one electron in the EG orbital. And this one electron is much higher in energy and it's not paired up, so it is much more reactive. So if we have a complex that is D6, reducing the complex to a D7, that is adding an electron through reduction in the oxidation state, would convert it into a labile complex, and then ligand substitution or reactions at the metal will be very quick. Then if we desired an inert complex, we could oxidize it and it would return to its unreactive state. So major points here are that this is a full lower energy orbital, and that is indicating that this will be inert. So a full or a half full low energy orbital is not reactive. So also D3 would be inert because it's half full. So I'll note that here very quickly. Low energy. That will make this complex inert. Whereas over here, we have a higher energy, not completely filled orbital, or even half filled orbital, and it is much more reactive. So now, there's something interesting that happens in this case right here, especially in this case. Now, orbitals do not like to be degenerate and unequally filled. Now, what does degenerate mean? Well, degenerate means that these orbitals would be the same energy. So there's three degenerate orbitals right here, or here. They all have the same energy, and so they're degenerate. Now, these are not a problem because they both have 2 electrons in each orbital. Whereas up here, we have, in our EG orbital, we have 1 electron here and none there. And so the metal or nature will not allow this particular instance to occur. These orbitals are going to have to shift in their energy in order for this electron configuration to exist. And this is one of the other reasons why D7 complexes that in a high field situation, high octahedral field, will be very reactive. It's because this orbital ends up shifting. And when that happens, it has to change the geometry of the metal. So that process has a name, and it's called a Jahn-Teller distortion. Jahn-Teller distortion. Now, Jahn-Teller distortions don't just occur in a D7 case with a high field. They would also occur in a D9 because these orbitals would be unequally filled. There'd be 2 electrons in this one and 1 in that one, for example, in a D9. They also occur when there's unequal filling in the T2G orbital. But Jahn-Teller distortions resulting from unequal filling in the T2G orbital in an octahedral environment are not as large and maybe, in fact, quite small, so that you would have difficulty measuring them. Whereas unequal filling in the higher energy EG orbital will have a large Jahn-Teller distortion. So that's why D7 is often used as an example of this effect. And it also played into the inert versus labile quite well. So this distortion will occur in every case that there is unequally full orbitals that originally had the same energy, that is, degenerate orbitals. So let's examine what happens to the energy levels in a Jahn-Teller distortion. And let's examine what happens to the geometry briefly. There's 2 options that could happen. But the first thing that we're going to do is shift the energy levels of the d orbitals here. So I'll draw those again down here. But this time, I'm going to shift the energy of one of these orbitals. And when given a choice, we'll shift the energy of the orbital that is occupied a little lower, because that will overall decrease the energy of the entire compound, and that would reflect reality because it's not going to adopt a higher energy state. It would need to adopt a lower one. So we'll have one orbital that's shifted down in energy, and I'll just draw this one up here far enough away so it's not interacting with my drawing of the electron here. None of this is particularly to scale, but the point is one of these orbitals shifts down in energy. Now, what orbital is that? Well, it could be either the x squared minus y squared orbital, or it could be the dz squared orbital. Either one, that can happen. So what is the result of that? Well, one of 2 things will occur. We have our metal, and we'll have our ligands. And our ligands are around the metal, and I'm going to draw solid lines for all of these, except in the case of bonds that would lengthen. So we have our same axial configuration here, but we may have a little bit longer bond in the equatorial. That is one way that a Jahn-Teller distortion can manifest itself. the lengthening of these 4 equatorial bonds and a slight contraction on the axial bonds. I think the one that's a little bit more common, though, is a lengthening of the axial bonds and not much effect on the equatorial ones, just because it doesn't affect as many ligands. I would have to read a lot more literature to back that up, but it feels like that's the case. Now, I'm obviously over-exaggerating this, so it's very clear. Often this distortion is very minute. And again, in the case of a D7, it would be more pronounced, and likely you would notice something in X-ray crystallography structures in that case. If there's unequal filling in the T2G orbital, you may not notice a change in the geometry. But the lengthening of some of these bonds does allow a little bit easier substitution. So not only do we have a reactive electron here, but we also have a bond that's a little bit longer due to this Jahn-Teller distortion effect. And when you combine these two effects together, it makes the complex much more reactive, much easier to substitute the identity of one of these ligands.